Okay, guys, today we're going to start a new chapter, chapter 10, and it's on really three topics. We're going to put three topics into this chapter. The first one that we're going to talk about today is called energy. So we're going to talk about the energy given off or absorbed in chemical reactions. The second part of this chapter, which we'll talk about next time, is on reaction rates, which really just measures how fast chemical reactions occur. And then we'll end the chapter by talking about chemical equilibrium. So that's kind of our plan. Before we get started today, I hope that you have your chapter 10 guided notes out and are following along and filling in the information as we go through these slides. So let's get started. Like we said, we're going to talk today about energy of chemical reactions. So there's this famous law in science called the law of conservation of energy. When we're talking about conservation, it means to save. So the law of conservation of energy means to save energy. You're supposed to write down the definition, and here it is. Okay. The law of conservation of energy states that in any chemical reaction, energy can be converted from one form to another, but it is neither created nor destroyed. So that last part, can we create energy, guys? No. Can we destroy it? No. But can energy change forms? Yes. And so here's what I mean. I've got a picture of this light bulb down here. If we have energy coming into the light bulb in the form of electrical energy, let's quantify this. Let's put a number to it. Say there was 100 joules, and joules is a unit that measures energy. So what if I had 100 joules of electrical energy coming in? How much energy should I have coming out? 100. We can't create and you can't destroy it. But it can change forms. So when you put energy into a light bulb, some of that energy is lost in the form of heat. The light bulb gets hot. It releases heat. And some energy is turned into light energy. So if I told you, if we measured the heat energy and it was 50 joules, how much light energy is being given off? 50 joules, okay? So goes back to that law of conservation of energy. You can't create, nor can you destroy it, but it can change forms. We went from electrical to heat and light. All right, we're going to talk about that today in terms of chemistry and chemical reactions. So I've got a picture over here of some matchsticks. There's one on the left that hasn't been burned. The one in the middle is currently burning, and the one on the right is finished burning. Which one has the most energy right now? Which one has the most energy right now? Why is it that one? Yeah, all of its energy that it had to begin with is still stored in the match, the top of the match here in this phosphorus, and in the wood. So there's chemical energy in the chemical bonds of the phosphorus and the wood. Now what's happening in the middle? What's happening with this one? It's reacting. The chemical reaction started. It's releasing that energy in a couple of forms again. What are we saying? Yeah, it's releasing heat. That's why a match is so hot. It's releasing heat. And what else is it releasing? Okay, so it's releasing heat and light. What about the one on the end here, this right side? It doesn't have as much energy, does it? But did we destroy the energy? No. It wasn't destroyed. It was just given off in heat and light. And so always remember that. You can't create nor can you destroy energy, but it can change forms. So we'll see that with chemical reactions. So let's get started. First of all, energy. Let's define it. It's actually pretty difficult to define. If I asked you what energy was, I bet you would have a hard time defining it. So let's look at the definition here. Energy. This is the best definition that I've come across. It is the ability to do work or produce heat. It's the ability to do work or produce heat. So in chemistry, guys, when we talk about energy, most of the time we're going to be talking about energy in the form of heat. So this is chemistry. We can do chemical reactions and it can release heat, and we can do chemical reactions that absorb heat. So we're going to be tracking the energy in terms of heat. Now work, if you take physics, we'll talk about energy in terms of work and what that is. But for the rest of the lesson, we're going to be talking about heat. So let's get into what heat is. Thermal energy. Thermal, guys, means heat. So this is just heat energy. Is the outward manifestation of movement at the atomic level. Let me say that again. Heat is the outward manifestation of movement at the atomic level. So to illustrate this point, I've got a picture down here. If I call this point A, right here, and this point B, and I asked you, at which point A or B are the atoms in that metal stake moving the fastest? What would you say? Yeah, hopefully you're saying that the atoms are moving fastest at A. How do you know that, though? Yeah, just based on the looks of it, this looks like it's at a higher temperature. This looks really hot, doesn't it? I mean, B is probably really hot as well, but it's not as hot as A. So what's happening is these molecules or these atoms at this point are moving faster. That's what leads to heat. So let me talk about what heat really is. Heat always goes from something that is hot to something that is cold. So it always goes from a higher temperature object to an object at a lower temperature. Heat is the flow of energy from hot to cold. So let me ask you this. When you are outside in the wintertime and you touch like a doorknob or some metal object and it feels really cold, why is it cold? Is it cold because the cold is coming into your hand? Or is it cold because the heat is leaving your hand? Remember the direction here of heat flow. It always goes from hot to cold. So when you touch something and it's cold, it's not that the cold is coming into your hand, it's that the heat is leaving your hand. When you touch metal, it's a good conductor of heat. Heat just leaves fast. And so it feels really cold. So always think of it like that. Or let me ask you this. Why in wintertime do we like to dress in layers? What are we trying to do?
Keep the warm air in it.
We're trying to trap all that heat next to our body because our body's at 98.6 degrees, way higher temperature than the air in the wintertime. So our heat wants to leave. So you wear a coat or layers and it tries to trap that heat next to you. Okay, so always remember, heat goes from hot to cold, and it's really the outward manifestation of movement at the atomic level. These atoms are just moving faster there. That's what it is. So let's look at energy changes in chemical reactions. Well, heat can either be absorbed or released in a chemical reaction. Next time you guys come, we're going to do a lab where you're going to do a few reactions, and some of them release heat, and some of them are going to absorb heat. And you'll be able to see the difference. Scientists call this change in heat energy enthalpy. Say that. It's kind of a funny word. Say it. Enthalpy. Okay? Enthalpy is given this symbol H. But in chemistry, we're really concerned about the change in heat energy, whether it was absorbed or released. So we're going to look at it, and you're going to see this symbol a lot. Does anyone know what this little triangle symbol means?
Delta.
Yeah, it means delta. It's a Greek letter. It means delta. Well, it means something. What does it mean? It means change. If you guys would make these notes in your books, that would be great, okay? So the delta, this little triangle is a Greek letter delta. It means change. How do you calculate it? How do you calculate change? Well, you take the final state and subtract the initial state. So final minus initial. Please write that. You're going to be using it this chapter. So when we talk about delta H, we're really talking about the change in enthalpy. And enthalpy really means heat energy. So I just always remember enthalpy is given the symbol H. It doesn't really have anything to do with how it's spelt here. I just remember that H it means enthalpy, but it means heat energy. Okay? So let me give you a definition of what enthalpy really is. Enthalpy is the amount of heat energy either released or absorbed in a chemical reaction. I've got a couple of pictures on the bottom of this slide, and I want you to answer this question. With this match right here, is heat energy being released or is it being absorbed?
Release.
It is being released. So heat is being released by this matchstick. Now when heat is released by something, the surroundings get hot or cold? The surroundings get hot because you're releasing that energy in the form of heat. It's making things hot around it, right? Now let's talk about this. It's cold pack around this guy's arm. Is this reaction releasing or absorbing heat? It's absorbing. This one is absorbing heat. So remember, which way does heat go? From hot to cold or cold to hot? Hot to cold. So how this cold pack works is it's taking the heat from this guy's hand or arm and it's absorbing it into the cold pack. Well, does that make his arm feel hot or cold? Think about it. His hand is now losing heat. That's going to make his hand feel cold. Okay. So when heat is released, it makes things hot. When heat is absorbed, it makes things cold. Okay. Let's talk a little bit more about enthalpy. Chemical reactions can have the following energy changes. There's two ways to classify chemical reactions in terms of energy. I'm going to put them both up right now, but we're going to talk about them one at a time. So number one, you're supposed to write quite a bit down here. The first classification in terms of energy for chemical reactions is called exothermic. Exothermic. We're going to break this word up into a couple of terms here. Exo. Underline exo. It means exit. So exo means to exit. Thermic. What does thermic mean? Yeah, it means heat. So what is heat energy doing in exothermic reactions? Is it being released or absorbed? It's being released because exo means exit, so energy or heat energy is being released. If you release heat energy, the surroundings get what? Well, they get hot. The temperature goes up. So if you do a chemical reaction and the temperature goes up, that's a sign that that was an exothermic reaction. And we want to track this heat energy. So we track it in terms of delta H. Delta H is a negative number. We'll talk about this later on today. But just remember, for exothermic reactions, the delta H is a negative number. All right. We good with that one? Let's contrast that to the other type of chemical reaction, which is called endothermic. Again, let's break this word up. Endo means to enter. Please make that note in your books. Endo means to enter. What does thermic mean, guys? It means heat. So heat is entering, or it's being absorbed by these chemical reactions. And the surroundings, if you take all the heat away from the surroundings now are going to feel what? Cold. You're taking the heat away from them. That heat is leaving. Now the surroundings feel cold. And the delta H is a positive number. Okay, so the takeaways from this slide. There's two types, exothermic reactions and endothermic reactions. Which one releases heat? Exothermic. That's what exo means, exit, so it's releasing heat. Which one obviously then means heat is being absorbed? Endothermic, because endo means enter and thermic means heat. Which one makes things hot? Exothermic. Which one makes things cold? Endothermic. Okay, please remember that. Okay, so to continue on with this point, chemists love to plot energy differences in chemical reactions, and they do it with these what are called energy diagrams. There's going to be a ton of questions on the next test on energy diagrams. This is something that you really need to pay attention to. So energy diagrams are used to plot the change in energy from the reactants to the products in chemical reactions. Remember a chemical equation, we have reactants and it goes to what? Products. So I'm always going to kind of abbreviate reactants with an R and products with a P. Here's two energy diagrams, A and B. Let's look at A first and then we'll talk about B. It's a graph, so let's look at what is being reported on the y-axis. What is the y-axis reporting here? Enthalpy. So it's heat energy. So we're tracking enthalpy. In these units called kilojoules, which is a unit of energy. The reaction time, or coordinate, is on the bottom. So we're starting with our reactants, and we're going to the products. So our reactants have this much heat energy. They're at 80 kilojoules. Our products have more than that. But in between, we see this, and you're going to see this with every energy diagram, there's this hill that it's got to go over. This hill, the difference from where you start to the top of the hill, is called activation energy. And it's given the symbol E sub A for energy of activation. Chemical reactions, in order for the reactants to form the products, you've got to give them some energy. Or else they'll just sit there forever. But if you give them this much energy, then the reaction will happen and you form the products. So the activation energy is the energy needed to start a chemical reaction. Okay, one other thing I would like you guys to be aware of. Our reactants had 80 kilojoules of energy. So they were right here. Well, when we finished, the products ended higher. Can we just create energy? No. So where did this energy come from? Yeah, sort of. From the surroundings. So what's happening is that heat comes in. And that heat energy is added, and so the products have more energy. That's where the reaction is gaining that much energy. It's from heat energy coming in. Guys, which chemical reaction is this? Exo or endothermic? if heat is coming in, which one means heat enter? This is an endothermic. Okay? This is an endothermic because heat is entering. Now, this energy difference from the reactants to the products, very important. Okay? It's called delta H. It's the amount of heat energy that was gained or lost in a chemical reaction. Well, this one gained it, so we went up. So our delta H is going to be positive. For endothermic reactions, that will always be the case. Your products will end at a higher energy, and that's because heat is coming in. Now, this is what confuses students. So let's see if you can wrap your minds around this. Students, here's where the misconception comes in. They think because in an endothermic reaction, heat is coming into the reaction, that it makes things hot. But that's not true. Okay? Heat is being absorbed by the reaction, which that heat energy is what is needed in order to form the products. So the products in the chemical bonds now have more energy. It's not necessarily making anything hot. It's just using that much energy to make the bonds in the products. Well, where does that heat come from? It comes from the surroundings, whether you do this reaction in a beaker, whether it's in water. Heat has got to be absorbed. And when you lose heat, what happens? You get cold. So these reactions make the surroundings cold. They make them cold. Okay, let's contrast that to this other energy diagram here in B. What do we call what we're starting at, guys? What is this? The reactants. What do we call what we finish? That's the products. What is the name of this hill right here? So from where we started to the top of the hill, what's that called? Activation energy. It's given the symbol E sub A, energy of activation. It's the amount of energy that you need to give the reactants in order for it to form the products. Okay, now this one is different. Notice how the products now are lower than the reactants. So what do we call this energy difference from the reactants to the products? What's it called? Delta H, change in enthalpy. Is it positive or negative for this reaction? It's negative. This one's going down, so it's going to be negative. Now, can we just destroy energy? That's what it looks like is happening. It had 100, now it's down to 50. Where did it go? It left in the form of what? It left in the form of heat. What kind of chemical reaction means heat exit? That's exothermic. So this is exactly what happens in an exothermic reaction. Now, if the chemical reaction is releasing heat, is that going to make the surroundings hot or cold? Hot. Yeah, things are going to get hot because it is releasing heat. So a perfect example of this reaction is right here. I've got a matchstick. Okay? My matchstick is my reactants. I've got some wood, I've got some phosphorus on the top. How long is it going to stay right here, guys? Forever. Unless you did what to it? Unless you strike it. Well, what does that striking it on the friction bar do in terms of what we just talked about?
Gives it enough heat.
It gives it the activation energy. Yeah, this matchstick is going to stay right here forever. It's always going to have this much energy unless you give the reactants more energy, you give them that activation energy, and then what will happen? Then it will start to burn and it forms the products. Okay? So when you strike this match, all you're doing is giving it the necessary activation energy. Now once it starts, it's going to continue on its own, right? Until all the wood is burnt up, right? Is this match an example of an endo or exothermic reaction? Exo. How come?
Because it's releasing energy.
It's releasing heat, right? If you fill, it's going to be hot. So it's releasing heat, that's exothermic. Now, does this matchstick that's burnt up now, this matchstick that's burnt up is down here. Does it have as much energy anymore? No. Well, we just talked about the law of conservation of energy. It says we can't destroy energy. Where did it go?
Into the air.
Yeah, it left in the form of heat and light. Very good. Okay, so that is energy diagrams. Are we comfortable with them now? Okay, if I asked you to label an energy diagram, could you do so? If I asked you to calculate delta H, the difference from where you start to where you end, could you do so? If I asked you, what is the activation energy? Hopefully you would be able to calculate that. Okay, let's see if we've got this concept real quickly. I've got this energy diagram up here, and it's labeled A, B, C, and D. Guys, quickly, what is A telling me? The energy of what? What is this line right here? The reactants. So that's the energy of the reactants. What is B telling me? It looks like it's about the same size as this hill. What is B? B is the energy of activation. Yeah, the activation energy. What is C measuring? From the reactants down to where we end? That's delta H. Very good. What is D telling us? The energy of the products. Okay, very good. Okay, I've got a short YouTube video. This professor does a great job. He's going to do a couple of chemical reactions, one endo and one exothermic. He's going to explain it, and he does a great job of explaining it, and also he's going to show at the end the energy diagrams for each one. Since you now know about endo and exothermic reactions, and you know about energy diagrams, I think what he's going to say is going to make a lot of sense. See if you can follow what he's trying to talk about here.
Hi, I've got a couple of demos loaded up and ready to go, and one of these is going to go ahead and give off heat, and the other one's going to have heat taken in. So I've got a beaker of water at room temperature. The red display shows that it's near 20 degrees C room temperature. And I'm going to lower the temperature, and I'm not going to do so electronically like with a freezer, and I'm not going to do it with ice. I'm going to dissolve a solid, which is actually going to promote an endothermic process. The solid is called ammonium nitrate, and I have the formula on the board, and I'll point that out to you in just a moment. What's going to happen is water molecules will surround this, and the reaction actually sucks in energy. So we're going to see a nice little temperature decrease here. So as I tap this in and it's stirring, we're going to see the temperature decrease. So on a good day, it'll drop down to about 0 degrees C. So it looks like we've got 7, and it's continuing to drop. The driving force for this reaction is the dissolving. The ammonium and nitrate ions are being surrounded by water, and it's going to a state of more disorder, as we say, and it's making the reaction happen. But in the process, think of it as like an energy vortex. Heat from the outside, heat from the water are sucked in to make the reaction proceed. Oh, and very good, it keeps dropping at 5. There aren't too many of these reactions, so this is rather novel. I also give it the nickname of the cold pack reaction, because these first aid cold packs, these little plastic bags with an inside bag, are available at pharmacies, and what will happen is if somebody bumps themselves like in the playground, somebody might come running over with one of these cold packs. What they do is snap it, and it's mixing the water on the inside with the ammonium nitrate, and it's spontaneously going cold, as demonstrated. Another little process loaded up here is just a simple combustion. I have some methanol, which is a 1-carbon alcohol, and I'm going to spray some on the counter and just go ahead and light it on fire. And flames are given off, a sign that we have heat, and I'll give personal testimony. It's warm. We have yellow, orange, blue flames here. It's combusting, heat's given off. That energy that's given off as heat came from chemical energy to begin with. Bonds are being broken, which costs energy, but then new bonds are being made and energy is being released. Let me go ahead and show you the processes up here on the board. The left side is the first reaction, and that is the cold pack reaction. The ammonium nitrate is a solid, and it's mixed with water and becomes ammonium nitrate aqueous. So these are two separate ions. NH4 plus is floating around, NO3 minus is floating around in the water. And at the beginning here, call it a baseline or the before enthalpy or heat, this is done at constant pressure, is around here. And what's happening is it's sucking heat in from the environment, from the water and the air. The analogy might be something like your checking account, where checking account starts here, then it's payday and a deposit is made. Ooh, that's nice. We increase the heat of the system, or the enthalpy, the heat at constant pressure. The time axis is simply just showing before and after. I have an arrow here going heat is taken in, so the energy of the system rises. Endothermic, or entering heat, heat enters the system. On the right side is that combustion of the alcohol. CH3OH is methanol. It burns in oxygen in the environment, and then we produce carbon dioxide and water. We start off with some high energy bonds, and then we end up with basically waste products, carbon dioxide and water. When you exhale, carbon dioxide and water come out. You extinguish candles with this. We use these in fire extinguishers, very low energy molecules. We start off high, we end down low. There's a little bit of an activation energy at the beginning, that hump that we have to get down over. Heat is given off in this process. Exiting heat, exothermic. What I'd like you to do is think about the delta H values for these two. One is going to be positive, one is going to be negative. Which one do you think is positive? Which one's negative? Have a look at the plots. See what's happening to the energy of the system. I wrote down that our endothermic is positive. We have an increase in enthalpy. You can see the before and after case. And our exothermic process starts off high, goes down low, so there's a loss of system energy or system heat. So that's a nice little couple of examples of endo and exothermic. I do want to point out the activation energy, which are the energies required for the reactions to proceed. The activation energy for this, the exothermic process, is just the little hump. These molecules need a little bit of energy. Think of it as the match at the beginning to get over the hump, and then it's all downhill from here. We call it EA, the activation energy. Now, many people will look at this and they might be thinking, hey, the activation energy is that little hump there, but it's not. The activation energy for an endothermic process would be the entire peak, the whole thing. And that's because of its being based on the definition of the activation energy, the energy required for the reaction to proceed. So we're starting here. If we give it just a little bit of energy, you might be thinking at the beginning, maybe this much, and that's not enough to go over the hump. So the activation energy is all the way over the top, and then you get a little bit back at the end.
Okay, so I think that you guys were able to follow that, weren't you? Okay, so even though that is a college classroom there, I think that you guys could understand basically everything he just talked about. In your guided notes, it wants you to draw an energy diagram for an exothermic and an endothermic reaction. So if you haven't already done that, let's do that now. Let's start with an exothermic energy diagram. Okay? What I would like to see is you label or draw some axes here. You've got to have a y-axis and an x-axis. On the y-axis, we're titling it energy, but I also want you to write H. You remember H means enthalpy. It's the amount of heat energy that is lost or gained in a chemical reaction. On the bottom, let's just title the x-axis reaction time. So again, we're starting up high on this one. Put on this line the reactants. Then we go over this hill. That hill is called the activation energy. We come down and finish below where we started, and we call this line the products. Let's label a couple of things. This hill, let's put E sub A. That is the energy of activation. It always goes from the reactants to the top of the hill. One more important thing to label. the energy difference from where you start to where we end up in the products. So this energy difference here is called delta H. For exothermic reactions, delta H is always going to be negative. We lose heat energy. Let's label one more thing. If we lost this much heat energy, see how the products are way lower? Did we just destroy it? No, you can't destroy energy. Where did it go? I want you to draw this arrow leaving. Okay? That energy wasn't destroyed, but it was released as heat energy. So heat is being released. That's why it's called exothermic. Exo means exit, thermic means heat. Heat is leaving. Okay, is exothermic, this releasing heat, is that going to make the surroundings hot or cold? Hot. So let's put that. Exothermic reactions make things hot. And hopefully that energy diagram makes sense. Now let's contrast that to an endothermic energy diagram. Again, we're going to start with our axes, the y-axis and the x-axis. We're going to put energy on the y. But really, I want you to put H. We're really going to track enthalpy, the amount of heat energy. Okay, this one is an endothermic, so we're starting low. Put reactants on that line. We go over this huge activation energy hill, and then we end up higher. Call it products. You'll notice for endothermic reactions, the activation energy, let's label it here. You always start from where the reactants are, and you measure to the top of the hill. That is the activation energy. For endothermic, activation energy is quite high. A couple more things to label. The energy difference from where you start, the reactants, to where this one ended is called delta H. In endothermic reactions, delta H is always going to be positive. You can see that the energy increased here. So our change in heat energy is positive. One more thing to label. Can we just create this much energy out of nothing? No. Where did it come from then? The surroundings. So let's draw an arrow coming in and put heat. We got that much energy because heat was being absorbed. And that's exactly what endothermic means. Endo means enter, thermic means heat. Heat is entering. Now, if you take the heat away from the surroundings, does that make the surroundings hot or cold? Yeah, you're taking the heat away from them. It's going to make them cold. Okay, so if you do a chemical reaction and you watch the temperature fall, that's a dead giveaway that it's an endothermic reaction. Okay, pop quiz. A heat pack kind of gives it away. You're going to make hand warmers next time. Endo or exothermic reaction? It's exothermic, right. How do they get hot? How does it feel warm? Well, it's releasing heat. We can't just destroy that much energy. Heat is being released, and that's what makes it feel hot. Okay, name kind of gives this one away. A cold pack you're going to make next time. Endo or exothermic? Endothermic. Endothermic. We can't just create this much energy. That much energy can't be created. It's being absorbed. So heat is coming in. That makes the surroundings cold. Okay, we're going to end with a few practice problems. Let's see if you guys got this. Practice problem number 1. It says, using the energy diagram shown below, determine whether the reaction was endothermic or exothermic. Also, I want a number. I want you to find delta H, but I want you to quantify it. Tell me how much delta H is, and also the energy of activation. I want numbers for those. Okay? So let me give you some time. If you're watching the video, please hit pause and try this one. See if you can't come up with those answers on your own first. Okay, so hopefully at this point you have tried it already, and you've got it all labeled up and you've answered those questions. Here's how I would go about solving a question like this. Now look at the energy diagram. We're starting right here. These are my reactants, so I would put an R there, or you can spell out reactants. Products are where we end, so I'm going to put a P right there. Now, we go over this hill. I know that hill is the activation energy, but we always measure it from where we start to the top of the hill. So this is my activation energy. Now let's calculate it, because I wanted a number. If we start at 50, guys, and the top of the hill is at 250, how much did I have to increase? 200. So my energy of activation is 200. But now I want units. What are my units here? Kilojoule. So we're going to put kJ and circle it. My activation energy is 200 kilojoules. Now, going back to the energy diagram, I started at 50. So I started right here, the reactants were at 50. But I ended, the products were at 100. So this is called delta H, the change in heat energy. If you were to calculate it, what would you say delta H is?
200. No.
The change in heat energy. It went up 50, right? So delta H is 50, and we're measuring in terms of kilojoules. But remember, if you ever get confused, the delta sign means change. So we could do final state minus the initial. Our products were at 100. If we subtract the initial, the reactants were at 50. What is 100 minus 50? Well, it's 50. So if you ever get confused, think about what delta means. It means final minus initial. All right, one final thing. Is this reaction endo or exothermic? And here's how I answer that question. If you look here, we gained heat energy. Can we just create that much out of nothing? No. So where are we getting this extra 50 kilojoules of energy? Well, it must be coming in. It must be coming in the form of heat. So if heat is coming in, which one means heat entered? That's endothermic. Okay, so it's definitely endothermic. Always, if delta H is positive, it goes up, it's endothermic. Okay, and one final thing, does this make the surroundings hot or cold? Cold. So if you did this reaction, it would get cold. Okay, very good. I think we got all the answers correct. We did. Practice problem number 2. It's exactly the same question, but it's a different energy diagram. So go through those same steps that I just did. If you're watching the video, please try it on your own. So hit pause right now and try it. See if you can't come up with the correct answer. Okay, guys, hopefully you've tried it at this point and you have some answers on your paper. But here's how I would go about solving this problem. A little quicker this time. These are my reactants, so I'd put R. These are my products, so I would put a P on this line. Okay? I always like to look at and just describe it from left to right. I'm starting right here, but the top of the hill is right there. So my energy of activation, or my activation energy, is how high this hill is. We're starting at 40 and we're going up to 100. How much did I have to climb? Start at 40, go to 100. My activation energy has to be 60. And we're measuring in kilojoules. So that's how high the hill is. Okay, then I come across. It looks like my products are ending up at 20, but I started at 40. So we went down. How much did we go down? 20. And so that's known as delta H. And it's going to be negative in this case because my final state is 20. My initial state was 40. So if we do 20 minus 40, that's going to be a minus 20 kilojoules. Okay? So my delta H is a minus 20. Now finally, can we just destroy that much energy? No. Can't destroy energy. Where did it go then? Well, this much energy left in the form of heat. Which one means heat exit? That's exothermic. That's exactly what it means. Now, if heat is being given off, is this going to make the surroundings hot or cold? It's going to make things hot. Okay, very good. How many of you guys got those right? Just curious. Okay, very good. We've got this stuff. Okay, let's see if we got them right. Exothermic, delta H is minus 20, and the activation energy was 60. Very good. Okay, I would like to finish at least the notes part of this video with this slide here. Okay, practice problem number 3. It says, using the energy diagram shown below, determine what A and C are referring to. Are they referring to delta H, or are they referring to activation energy? You tell me which is which. Let me give you a second to think about that and to answer it on your own. So please hit pause. All right, hopefully at this point you've tried it. But let's look at what A is really measuring here. So from where we start, from the reactants, to the top of this hill, what is that known as, guys? Activation energy. How do we abbreviate activation energy? Because it's kind of long to write every time. E sub A. So A is measuring the energy of activation. Okay, now what's C measuring? C looks like it's going from where we started with the reactants, and it's measuring how much the products gain. What is that called? That's measuring delta H, the change in heat energy. Okay, how many of you guys got those two right? Okay, very good. Now I didn't ask you about B, but what is B? Let me see if I can help you understand what B is. Most of the time we go from reactants to products. But what if we reverse this reaction and we went the other way, from products to reactants? What would B be if we reverse this reaction? Isn't this the energy of activation for the reverse reaction? So if we went this way, wouldn't B be the activation energy? And that's what it is. But anyway, so hopefully that makes sense.
So would it then turn to exothermic if it was endothermic?
Yeah. So in the reverse direction, this would now be exothermic because we're giving off heat. Good. Okay, a couple more slides. Stay with me. You can do this. This is an interesting question, and it's one that students get wrong all the time. So let me see if I can correct some misconceptions here. This is the phase change diagram for water. Okay, so the substance is water. We have ice right here. Let me draw an ice cube. We've got water in the liquid phase, so let me draw a little puddle. And we've got steam. So there's the water molecules in the gas phase. It says which phase changes are exothermic and which phase changes are endothermic. You got to think about this. Let's start with ice to water. So we're going to melt. In order for this ice cube to melt, does it have to absorb energy or release energy?
ice to melt, it absorbs energy.
Okay, in order for this ice cube to melt, doesn't it have to absorb energy? Doesn't heat have to come in? Which one means heat entering? This is an endothermic process here. Okay, what about water going to steam? Again, the water has to gain energy in the form of heat. If you heat up water enough, it will go to steam. So that, again, is endothermic. And we kind of can understand that energy is plotted on the x-axis here. Energy absorbed is going that way. So what about going left? Going left is going to be energy released. Let's see if we can understand that. If we're at steam and we want to go to water, does the steam have to add energy or release energy? Yeah, it's got to lose energy. It's got to lose that energy. Which one means heat exit? Well, that's exothermic. Okay? And same thing when we go from water to ice. Doesn't this water has to lose heat energy? It's got to lose it. When it loses that heat energy, the molecules slow down. It becomes, and you can freeze it, and it becomes ice. So again, this is exothermic. So always ask yourself, what does heat have to do? Does it have to be released, or does it have to be absorbed? Okay, energy review. Let's just quickly review everything that we just talked about. Did you learn what energy is? What is it? Yeah, it's the ability to produce heat or do work, right? In chemistry, we're more concerned with what? Heat. So it's the ability to do work or produce heat. Did you learn what the law of conservation of energy is? Can we destroy energy? Can you create it? Does it change forms, though? Yes, it does. Did you learn what an exothermic reaction is? Exo means what, guys? Exit, and thermic means heat. So heat is being released. Endothermic. Did you learn what an endothermic reaction is? What does endo mean? Enter. And thermic? Heat. So is heat being released or is it being absorbed? And it is being absorbed. Okay, energy diagrams. Are you guys comfortable with energy diagrams? Do you know what they mean? Do you know, if I pointed to a part on this, could you tell me what it meant? If I asked you to find delta H, could you calculate it? Activation energy. The energy of the reactants, the energy of the products. Hopefully you can. Enthalpy. It's kind of a weird name, but what does it mean? It means heat energy. What symbol does it give? Is it given? A capital H. Okay. Do you know what activation energy is? The energy needed to start a chemical reaction. If you look, it's that hill. So you could calculate it, right? Finally, 2 more questions. What type of reactions make the surroundings hot? Exothermic. Very good. So this is an exothermic. And last question, which type of reactions make the surroundings cold? Endothermic. Okay, good job, guys. I hope that makes more sense. Before we stop the video, I wanted to give you some more practice with these types of problems. So I created an energy diagram worksheet in the student workbook. So let's go there now. Again, it's titled Energy Diagrams Worksheet. Let's get that done, and hopefully this video helped.